introduction. Thank you for the organizers for this invitation to this great workshop. I want to talk about the fundamental property of hydrodynamics and prove a theorem that explains this property. Now, what is the situation I have in mind? Consider some many body system where you have n local conservation laws. So you have densities, conserved densities, u alpha of x and t. Right? Alpha is the index, and x and t are space and time. Now, conservation means that these guys satisfy a continuity equation, d dt q alpha of x and t plus dx j alpha of x and t is equal to 0, right? That's what conservation law means. Now, let me rephrase this and point out a property of this system of equations. Namely, let me write this as follows. First of all, let me introduce a vector, q, that has all these charges in them. Then I can write down dtq plus dx j is equal to 0. I omit the arguments, right? It's just a way of rewriting this. And here, now I use the chain rule to rewrite this as follows. ddq plus j dx q is equal to 0. And this j here is nothing but the Jacobian of the current, because these currents actually depend on the local densities. They depend on space and time through the local densities. So that's the assumption that I do. We have heard about this yesterday. It's the usual hydrodynamic assumption. So J is the current Jacobian. J with matrix elements J alpha beta equal to dj alpha dq beta. Okay? And it's a function of space and time through the densities. So that's the kind of system I have in mind. Of course, there can be a diffusion term here, but this will not play a role in what I'm going to do. So now this Jacobian is a matrix. It has eigenvalues. Eigenvalues, the alpha of j. These are the characteristic velocities. We have also heard about this yesterday. These have two interpretations on the macroscopic level, on the PDE level. These are just the velocities of the characteristics. And microscopic mean these are the velocity of local perturbations in a stationary background. Perturbations in a stationary backgrounds with fixed values of these conserved quantities. Now, since these are velocities, they obviously have to be real numbers. So for a physical system, these V alphas have to be real. But J is not a priori clear that J has real eigenvalues. So there must be some underlying principle that tells us that J has only real eigenvalues. And this comes from the following fact. So write J as function of the chemical potentials, generalized chemical potentials, mu alpha. These are the chemical potentials that are just canonically conjugate to your conserved charges, right? So they're also a function of x and t, assuming this local equilibrium. And then it turns out that, so let me call this j tilde as a function of mu. So then it turns out that j tilde alpha beta is equal to j tilde beta alpha. So if you write this function of these chemical potentials, then you will see for any system, I promise you, that you have ever seen for any field system, you will see that this matrix is symmetric. So, and that's the fundamental property that any system that can be described hydrodynamically has to satisfy. So that's a property I want to keep. This stuff I will erase, but I will write it down here. So let me mark this with a star. Okay, so now how can one see this? Well, it is certainly known for a very long time. I don't even know who first made this observation. It's really, I mean, a kind of standard law. But in actual fact, the first mathematical proof that I've seen is actually from a paper that's not so old. It's from 2003. Of local perturbations, of characteristics, the macroscopic. The characteristics, yes, of this PDE, right? Just see it as a partial differential equation that you can solve by the methods of characteristics, and then this will be the velocity of these characteristics, just the slope of these lines in a plot. So that's just PDE theory. It's something. Well, I mean. Yeah, it's like a group velocity, but but this would be the microscopic picture, right? On macroscopic picture, yeah, okay, yeah, you can see it as a group, but yeah, it's a kind of, but not really, because if you have a group velocity, you have some kind of bunch on a macroscopic scale, right? And then this will broaden a certain way. You really have to look at a specific point and see how a specific point at a given density, how this moves in space. That's what this characteristic will do. So to make it more clear, just take one conservation law, right? Then you have a profile, rho of x and t, and now you fix a certain value of rho, and you look at the curve where this value of rho remains constant. This will be a straight line with a slope given by v. So that's the meaning of the characteristic. And then for more conservation laws, it's a slightly more complicated interpretation, but it's analogous. Okay, so Scott and Valko, 2003, they proved this relation for a very specific interacting particle system, classical stochastic particle system, with a very special property, namely the stationary distribution. The stationary state was factorized, had a factorized stationary state. Then, at that time, I met Valentot in Hungary, and we discussed this thing. And later, I worked with Raphael Grisi from UFABC on this problem. And then in 2011, we published a paper, Grisi and me, where we proved this relation. Actually, we proved that this comes from a more general relation. Namely, it comes from a relation of the sort J alpha 0 Q beta is equal to Q beta 0 J alpha. Again, for classical systems, stochastic systems, but of very general nature. So this is also mathematically rigorous proof. And from this, you can derive this relation under the additional assumption of a canonical ensemble, a grand canonical ensemble with its chemical potentials. So, sorry? Capital Q, sorry, thank you. Yes, capital Q is the integral to x. And it's conserved, so it doesn't depend on t, right? And J is, I should have said this as well, is the integral dx J alpha of x and t. And this is in the stationary distribution, right? So evaluate in the stationary distribution. So from this, you get this statement by this local grand canonical ensemble. It's an extra assumption. Yeah. Oh, no, they're not. It is the same because a macroscopic perturbation really is a point. Imagine you have a macroscopic profile that is just the delta peak, right? Then this delta peak, or let's say something like a very, very narrow concentrated peak. Then it will move with the same speed. And this is the macroscopic analog of this microscopic perturbation. So if you take a macroscopic peak and take the limit where the width goes to 0, then it is the kind of macroscopic analog of a microscopic perturbation. Yeah. But I mean, this is a classical equation, right? So yeah. Okay. So now so we are still here in the classical picture, right? Classical particle systems. And then in 2000, hang on, was it? 16, yes, right. You should know, Benjamin. 2016, there was a nice paper by several authors, Castro, Alvaredo, Goyon, who's here, and Yoshimura, 2016, who have a relation like this for quantum system. For quantum systems. So let me keep this here as well. Give it 2 stars. And then, very recently, there was a paper that actually derives this relation from an even more fundamental charge-current correlation function. And this is the following paper. This Bernard, 2019. So we are already in the present, where they find this again for quantum systems, but it doesn't really matter. It works equally well for classical systems. I think you also point this out in your paper. So this is now really a space-time correlation identity. And from this, you get this 2 under some assumption on decay of correlations. So both this and the derivation here require some assumption on decay of correlations. And all of these results require translation invariance. So now you see why I give this talk on the blackboard. There are several details that are important that on slides I think would quickly disappear and which I want to maintain. So we have a relation 3. Two. I give it 3 stars. So really the most important point is translation invariance and some assumption on decay of correlations, which I will specify. Here. So what I want to show you now in the remaining time is a generalization of this result and a clarification of precisely what is valid when. So this will be the main result, the theorem. I will state it and then indicate how it's proved. This. No, it's a trace of a stationary density matrix. I will specify it now. Yeah. Yeah. Because exact integration creates boundary terms which have to decay. You will see. Yeah, right. It's okay. Maybe I should say that already 2 also requires some decay of correlations, actually. Yeah. Yeah, no, that's true. From 2 to, no, I see what you mean. From 3 to 2, indeed, you can go just by integration. That's correct. Yes, yes, right, yeah, right. But you cannot easily so quickly go back from 2 to 3. That's the point here. And also, the assumption on decay of correlation is actually slightly different between the 2. So, okay, so now the main result, let me kind of so the main result is the following. There is a generalization of this relation 3 for non-translation invariant systems. And I will write down what this generalization is, of course. But first, let me give you the essence. Non-translation invariant systems. Which requires only either a canonical distribution, or decay of correlations, which I will specify, and no further assumption at all. Except, of course, that these expectations have to exist, right? So you have to choose operators such that the thermodynamic limit of these guys will exist, right? But this is really the only tacit assumption that I will make. So this is basically the result. And of course, I have to write down what precisely it is. And for this, I have to introduce some notation. Yeah. Yes. Yeah, this is exactly, but if you integrate, because the conservation law, it becomes automatically time independent. So let me describe precisely the setting. Now, so first of all, let me say this result will be true for purely quantum systems, will be true for classical Markovian systems. It will also be true for dissipative quantum systems with Lindblad dynamics. And it will be true on the lattice and will be true in continuum. So it is very general, but just to be specific, I will work on the lattice in the quantum language. Otherwise, notation becomes so general that you lose track of what actually this is about. So I take a lattice, and also it works in higher dimensions, but again, I will write it down only for one dimension. The generalization is kind of immediate. So I take a lattice of L sites. I have a Hamiltonian. HL. And I have a density matrix rho L. Matrix rho L such that HL and rho L commute. That means rho L is a stationary density matrix with respect to this Hamiltonian, right? So this is my input. And then I assume, as I said, I assume that the expectation that I'm going to consider will have well-defined thermodynamic limits. That's all. So that's the start point. Then, of course, I have my n conservation laws. That means that I over h bar, HL commutator with this qk alpha of t is equal to j alpha k minus 1 of t minus jk alpha of t, right? That's what conservation law means. So this is my setting. And again, the capital Q will denote the sum of all these local charges, and the capital J will denote the sum of all these currents, sum of the lattice. And I consider the following quantities. I consider the dynamic structure function, SL alpha, a kind of analog. But as I say, it's not translation invariant, so it depends on two coordinates. uk alpha of t, ul beta of 0. And then the following current charge correlators, CL alpha beta of K, L, and T will be JK alpha K of T, U beta L of 0. So this is time argument, right? And the commutator of this, and the commuted version, K, L, and T, this will be equal to Q alpha K of T, J beta L of 0. So I interchange the role of J and Q in this commutator. Since we have a quantum systems, these things on no translation variance, these things are not trivially the same. Okay, so this is the quantity that I consider, and now I just use my conservation law, and I find that the time derivative S dot is just equal to two different quantities. Namely, it's on the one hand, it's equal to jk minus 1 alpha of t minus jk alpha of t, u beta L of 0. That's one equality by just applying it to here, but I can also apply the commutator to the q, by applying it to this guy, but I can also apply it here to this guy, but I can also apply it to here. So it's also equal to q alpha k of t, jl minus 1 beta of 0 minus jl minus 1 and jl of 0 beta. So these are two equalities. They simply follow from the fact that I can use my commutator on either this or on that, right? So this is a kind of trivial statement, but nevertheless, it is interesting because by subtraction, it implies the following fundamental charge current correlation identity, which is, as I say, kind of trivial, but very useful. Minus CL of K, L, and T plus C tilde alpha beta of K, L minus 1 and T minus C tilde alpha beta of K, L, and T, right? So this is a formula that I will use. And let me recall, there's no assumption at all, right? Just use my setting. Now, let me explore the consequence of this relation. So first of all, let me look at the total charges. Let me introduce AL alpha beta of K and T. It's just a summation, of K and T, just the sum L, CL, L alpha beta of K, L, and T, and the analogous quantity with the tilde of L and T, which is the sum over all K, T tilde alpha beta L of K, L, and T, right? So these guys I look at, and now I use my conservation law and stationarity, which will tell me that these guys actually do not depend on K and T, they're constants. So this will be a constant, A alpha beta L. This will be a constant, A tilde alpha beta L. So this just follows from stationarity and from the conservation law, nothing else. So these guys are constants. Okay. So this is for charges. Now I look at space averages. I consider the following quantity. PL alpha beta of R and T is equal to 1 over L times sum over K CL alpha beta K plus R of T. So again, this is not translation invariant. This is not just a function of R, right? But I take the sum over the whole lattice to make a space average. And similar for the tilde, of course. And T. So now these are these guys. And what can I say about them? Well, if my system was translation invariant, I would go back to the translation invariant scenario and would derive the results that are on the left-hand side. But it's a bit more complicated. To treat these quantities, I have to use a trick. And this trick is the following. I introduce an auxiliary function. Let me just, yeah, that's enough time. I introduce an auxiliary function It's a bit technical, but I want to write it down anyway. GL alpha beta of K, L, and T, which I define to be the sum over K prime from 1 to K, C tilde alpha beta L of K prime 0 and T minus C alpha beta tilde L of K prime L and T. This G is refined with the tilde functions. I omit the tilde because I don't need another G. So this object I look at, and I also look at the space average, L alpha beta of R and T, which is 1 over L times the sum from K from 1 to L, GL alpha beta K, K plus R T, right? So these guys are all periodic because my lattice is periodic, right? That's all, but not because of translation invariance. So now I can use this identity to express the formulas as such are not so important, but I think they will illustrate the idea. So I use this auxiliary function to write the following. C alpha beta of K, L, and T is equal to C alpha beta L of 0, L, and T plus GL alpha beta K, L, and T minus GL alpha beta of K, L minus 1 and T. This is something that you can easily check. And then there's a similar relation for C tilde, which can also express in terms of C tilde at, so this will be like C tilde alpha beta of K 0 and T plus a similar term, right? This is not so important to write down. So my trick is the following. I introduce the auxiliary function and I write down this simple identity. The same G, right? So the tilde function has the same G, right? So it's important here. And then I can take summations over space, and I get the following. I want to keep. Okay, so I take space averages, just taking sums, that's a trivial step now, and I find the following. I find something that is surprising, namely I find that my function B, my space average alpha beta of R and T is equal to 1 over L times this constant AL alpha beta plus the space average G of R and T minus JL alpha beta of R minus 1 and T. Okay, that's something that you find. You also find BL alpha beta tilde of R minus 1 and T is equal to 1 over L tilde alpha beta L plus the same thing. So you subtract and you find EL alpha beta of R plus 1 and T minus E tilde alpha beta of L, R, and T is equal to a constant 1 over L alpha beta. It's not very good notation. Let me call it, that I did not use yet. Call it X alpha beta, where X alpha beta L is just the difference of these two constants. A alpha beta L minus A tilde alpha beta L. So this is, it may not look like it, but this is exactly the charge correlation identity, somewhat similar to this one, but with an extra term and on the lattice with the space average. So let me write down what this is. This is equal to J0 alpha of 0 Q beta minus Q alpha J0 beta of 0, right? That's what this difference is like. So this difference that we have over there is equal to this difference of these space average correlation functions. And important, this is true. So this is a constant for all R and T, right? So there's a constant. This does not depend on R and T, the left-hand side, this difference. So still no assumption at all, right? So this is a completely generally valid result. Now let me make some assumptions. So first of all, I look at the decay of correlations. Will be 1, right? Such that the limit where R goes to infinity of B, R, and T, and similar for tilde, limit R to infinity B tilde alpha beta of R and T is equal to 0. Now, why can I make this assumption? Well, this is really just rephrasing the Lieb-Liniger bound, the Lieb-Robinson bound, because this is a correlation function, right? And I keep T fixed, right? And I just send R to infinity, my distance between the 2 points where I make my measurements. And of course, I would expect usually for this to decay. So this is a very mild assumption. Now, if this is 0, then it follows that this will be 0. And it follows that alpha beta over L, limit L to infinity, this has an L in it, sorry, I should have this, is equal to 0. And then it implies also that this is equal to 0, right? So if this is 0, then this is 0. And this is the generalization of 3 to non-translation invariant systems. Systems without translation invariance. So let me write it down. E of R plus 1 and T is equal to E tilde of R and T, beta, right? So now let me, so this assumption of decay of correlation, I assume this to be 0. Now let me make a slightly different assumption, namely let me assume that limit where L goes to infinity, L times EL of alpha beta R and of L over 2 and 0 minus E tilde L of L over 2 and 0 tends to infinity. That means that this correlation difference should decay faster than 1 over L. It's not exactly the same assumption as this one, right? So it's a stronger assumption because, yeah. So in this case, it follows that XL alpha beta itself is 0, not just this limit. And then you also get statement number 2. for non-translation invariant system. Non-translation invariance. Okay, and then the last one. So if you additionally assume translation invariance, you get these results back. So this is the generalization. Now the last one, last assumption is the charges commute, Q alpha, Q beta, commutator is equal to 0, and also commutator with rho equal to 0. And then I get, with this kind of canonical ensemble, I get result number 1. So with this of grand canonical form. And canonical form. And canonical. And if I use a canonical matrix, then this will be true even without decay of correlations. That's another simple computation. So that's the results I want to present to you. So the generalization of this a new charge current correlation identity that's valid for non-translation invariant systems, and then completely generally proves this relation that appears in hydrodynamics with the conditions that are necessary to satisfy it, also made explicit. Thank you. Nothing, just that this commutes with H, that's all. Yeah, right, stationary, that's all. Yeah, right, yeah. Yes, right, yes. Sorry, yes, right, yeah. Yes, right, yeah. Correct, yes, yeah, right, yeah. Well, in the classical setting, I can give you hundreds of examples. I mean, basically any stationary state where, in this case, you would have a stationary distribution here, and this would be the generator of your Markov process. For the quantum case, yeah, you can take something that's driven by Lindblad dynamics, for instance, a density matrix. So you have some dynamics that have a unitary part and a Lindblad part, and look for the stationary solution. This would be something of this form where the rho is not thermal, not just a function of H. Of course, this is truly the case if rho is just a function of H, right? But if it's not, then Lindblad dynamics would be an example.
Invoked the...
No, this is an assumption, right? And
this is an assumption, okay.
Yeah, I just justified with the Lieb-Robinson bound that this is natural to assume that.
Have a classical system?
Well, yeah, I mean, it's valid also in classical system. That's basically a statement. You see, if you have a stochastic dynamics, then basically also there, perturbations spread at most ballistically. That's usually the case, right? Anyway, just 1 second, as I say, this might not always be true, right? So in fact, one can give examples where this is not true. So it's not an empty assumption, right? It's just a very general one, a generic one. Here, if they don't commute, okay, look, in this case, I would say it's sufficient, right? Not sure it's necessary. This is necessary and sufficient for that to hold, right? But here, I don't know. Question. If they don't commute, then you get from well, first of all, you get problems with this condition if they don't commute, right? This is a complication, but okay, you can just take the unit matrix here and take some kind of grand canonical thing with non-commuting objects. This you can do, but then you get extra terms which might be 0, but I don't know how to show it. We have some reasons, we have some examples. If you take SU2, for instance, then you can show that these extra terms actually vanish, right? But we don't know how to do it separately. So you could, for instance, take as rho, you could take just the exponential of Sx plus Sy plus Sz, right? Or some combination, and then something else to, but it's not so easy to actually get an example where they don't commute.